You're live. Okay. Okay. Is my voice also okay? Okay, good. Good afternoon, everyone. Welcome to another lecture 15 in computer architecture course. Today, as we promised, we're gonna cover flash memory and solid state drives. Today and tomorrow, actually, both days, we're gonna cover these topics. Today, I'm gonna mostly focus on storage architecture, like how SSD, is working, how we manage SSD. In order to do that, also, I will provide some background about flash memory. But tomorrow, we're gonna have deep dive into flash memory to understand reliability issues of flash memory and how we can basically overcome that. So, any questions? So then we can start. So we have actually published a lot of papers in this topic. MQSim is actually one of the papers that we design a simulator. We may have some lectures about MQSim also later on. Some of you might have worked with MQSim. I guess you actually work with MQSim in one of our courses. But yeah, MQSim has been used in a lot of our researchers, and other people are also using. Is actually a state-of-the-art simulator for SSDs that we're going to learn about more. I'm going to cover some of these papers today, but not all of them. For some of them, we're going to actually have some dedicated cutting-edge research presentation later. Like GenStore and Megis, I think John actually presented a little bit about them last week. And so, yeah, so this topic is actually quite exciting, and we have done a lot of works, and we always look for, interested students. If you want to continue this line, you can just reach out, and we have a lot of ongoing projects in this topic. Okay, so I'm going to provide an overview on SSD organization first, and then we're going to how we do address mapping and garbage collection, which are one of the most important internal tasks inside the storage. Then we will get to I/O scheduling in the end. And if we have time, we will also go into flash memory array parallelism at the end of this lecture. So modern SSD architecture is a complicated system that consists of multiple cores, hardware controllers, DRAM and NAND flash memory packages. You can actually see them more or less in this picture. Like these are NAND packages. 4 of them is this side of this PCB. We have also 4 NAND packages. The other side is actually the SSD architecture for one of the Samsung devices. We also have LPDDR DRAM that you can see here, and also this SSD controller, which has several cores, here 3 cores, for example, and there are also some hardware flash controllers. And each flash controller actually do request handling, ECC and randomizing, and has also encryption engine. We're gonna learn about all these modules in this lecture. So for the SSD controller, there are different basically components or different steps that we need to do. One of the first one is host interface layer, HIL, which the goal for HIL is to implement the interface basically protocol. Like if it is SATA, like the pass, and also NVMe that we have today. So that's the job for host interface layer, to provide interface such that the host system, like the CPU, can communicate to the storage device. In addition to that, we also have FTL, which is flash translation layer. that has a lot of important actually duties like data cache management, address translation, garbage collection, word leveling, refreshing, and so on and so forth. We're going to learn about the different jobs of FTL in this lecture. We also have flash controller, as we discussed. And flash controller is actually also part of this SSD controller. And in each flash controller, we do ECC and randomizing. And these flash controller are managing. Each of them are each of them manages NAND flash package, and NAND flash package can also consist of several NAND dies, which we're going to also learn today. So in the DRAM module that we have, we keep different information. One of them is host request queue. So essentially, you need some queues to keep the request in that DRAM. We also have write buffer in that DRAM, which we also learn about it, like what's the reason about it, and also very important actually, the logical to physical mapping. That kept actually one of the capacity hungry component in that DRAM, that most of the DRAM actually structure is allocated to logical to physical mapping. And we're going to also learn about it later. There are also some metadata regarding PE cycles, like program array cycles, that has been used for other other operations, such as garbage collection, such as word leveling, and refreshing, essentially. Okay, so now let's walk through this SSD controller to see how it works. And for that, we start with the write operation. So assuming that host system sends a write request to the storage system, and we want to write essentially like some pages inside the storage. So communication with the host operating system, and basically the HIL, this layer receives and returns request. This is via a certain interface, SATA or NVMe, that I already explained. We're going to also learn a little bit about NVMe at the end of this lecture. And the host IO request includes request direction, whether or not it's read or write. It also has an offset, like you need to show like what's the start point of the sector address. So from the OS, like the IO file system, basically the storage is considered as a logical view, is like the big array, let's say. So like it's a big array, and you have chunk of like pages in that big array. And in order to send the write request, the OS only needs to say what's the offset, in that big array, from which point I like to start to write. So that's why we need this offset. And then you need to tell storage about the size, like how many sectors you want to write. So by specifying the start point and also the number of offsets, the number of sectors, you can actually finalize your request. And all these are typically aligned by 4 kilobytes. This is actually from SSD domain. So in the past with hard disk drive, we were actually using the sector size, which was 512 bytes. But with the SSD, basically people realize that if we increase the page size, that can actually help better performance and energy efficiency. So they work hard and also at the OS level, and they increase the page size to 4 kilobytes. That doesn't mean that we cannot have sub-page access. So you can still send, for example, requests to SSD with like sub-page, like sector size, but those are like costly for storage. And also in addition, like the flash memory, I think we have discussed this last Thursday, that essentially this is the view of the storage, that we have separate memory, like we have memory, main memory, and then we have storage, which has the second level of hierarchy. And we also discuss if we can unify them in one like unified memory architecture, and that unified memory can have different memory devices. It can be flash memory, hard disk drive, DRAM, and also PCM, for example. So in that domain, actually, you can think of having like byte access to the flash. So it doesn't really, flash memory doesn't have to provide, like page access granularity. It can be also sub-page. Yes, it has some overheads, of course, but basically it's a matter of like trade-offs. So in that system, you can think of what are the trade-offs, how much performance you can get if you provide more fine-grained access to your flash memory, and what are the overheads, and then make a decision, basically. Any question about HIL level of this write operation? Okay, good. So once we are done with HIL, then we need to get to the FTL. So first, we just buffer data to the write buffer. So the data that you want to write, you need to buffer it. And that's why there are a couple of reasons for that. One of them is that writes in flash memory are quite costly in terms of latency. And if you want to pay the latency for writes every time, you need to basically, cause a lot of performance overhead to the system. So most of the time, you just write to the write buffer and then send the acknowledgement actually to the host system. And then the write operation can happen in the background. So that's why this write buffer is actually quite essential to reduce the write latency. It also enables flexible I/O scheduling. Like for example, if you consider that you want to schedule between writes and reads, so reads are relatively faster, but writes are quite slow. So in the end, you always think of prioritizing reads over writes. But once you have write buffer, then you have some write operations that they are faster, and as well as reads. So now you have more flexibility to make a decision. Sometimes you can actually schedule writes over reads. So that's why flexible I/O scheduling here is actually quite important. And this write buffer can also be helpful for improving lifetime, meaning that basically recall that all these non-volatile memories, I mean, flash memory was also kind of emerging in the past. Nowadays, it's not emerging anymore, but it has endurance problem. So it can afford limited number of writes or program erase cycle. We're gonna learn about it also later. But essentially, if you have write buffer, you can actually do some writes in that write buffer, and it can reduce the number of writes that in the end you need to write to the flash, if you have good locality in your writes. And that's why this is not so likely. So the locality that you get at the level of storage is not that high. So most of the time, you don't really rewrite to the same logical address in a relatively near future. So that's why this improving lifetime is not that likely with this write buffer, but still you can get some improvement. So, but it has some issues. Like this write buffer has limited size, tens of megabytes. The main reason is that, remember that I said once you write to the write buffer, most of the time you can actually send the acknowledgement to the host system. Even though there are some write operations that you can specify them as synchronous, meaning that the system has to write them to the flash and then you receive the acknowledgement. But for many other writes, you can just write to the write buffer. But that doesn't mean that write buffer can lose your data. So remember that the storage system is considered as a persistent memory. So it should keep your data. But write buffer is actually DRAM. So if you have some sudden power cut, for example, that DRAM can just lose your data, right? So in order to avoid that, in enterprise SSDs, we have some capacitors. And those capacitors provide enough charge such that, whenever you have power cuts, they can actually provide enough charge for the staging operation, like writing back dirty data in that write buffer to the flash memory. So that's actually quite essential. And because of that, you cannot actually have big DRAM buffer, because bigger DRAM buffer, you need basically larger capacitors. And those capacitors are costly in terms of area, in terms of power, in terms of many, many other reasons. So that's why actually people are trying to keep this write buffer as small as possible. But that being said, there are also some works that they try to build write buffer with other technologies that they are non-volatile. Like, for example, people try to build a write buffer with the phase change memory. So you can check out actually some papers that they try to make it like a hybrid phase change memory and flash technology. There are also some other works, actually they are at the prototype of industry. I mean, not prototype, actually they are commercially prepared, that people use SLC mode of flash as the write buffer. So when you have your flash memory in a TLC mode, which is like you can store 3 bits per cell, it's actually quite slow. But then you can actually consider that you have a small flash memory, like some buffer, as in terms of like built by flash memory, but that's only used as the SLC mode. So then that flash memory in SLC mode can be used as a write buffer or cache of the TLC, your flash memory or QLC. So people are trying actually to increasing the size of this write buffer by doing some tricks, basically. Okay. Another operation in FTL is actually address translation. We're going to learn about a lot today, but one of these core functionality is actually for out-of-place writes. So whenever you receive an update inside the SSD, you don't really update the same location that you have been written. So you need to basically find another location and write to that. So that's why we call it out-of-place writes. We're going to learn about the reason. And that's why you always need to keep the mapping table. So there should be a table tell you that each logical address from the OS is mapped to which physical location. So that's actually one of the main, the portion of this DRAM. So like the most of the DRAM space is actually allocated to this logical to physical mapping. So mapping granularity is usually 4 kilobytes. And which means we need to keep like 4 bytes for each 4 kilobyte page. And that's, we get to this 0.1% of the SSD capacity. And that's why usually the DRAM capacity that we have in enterprise SSDs is actually around 0.1% of SSD capacity. Like if SSD capacity is 1 terabyte, your DRAM is around 1 gigabyte, for example. Any question? Yes. Yes. Yeah, but not all of them. Those parts that you have changed them, basically, But there are some parts of flash memory that you keep actually, they are there for mapping, basically, so that's your definitive storage for that. That's a very good question. Yes. Yes. Map it to another page. Yeah, one of the reasons. That's one of the reasons, but there are also other reasons. But we're going to get to that in later lectures, later slides. Yes, but keep your question for that. Yeah, I mean, that's, yeah. So if you know about like the number of pages, number of blocks that you have, you almost need 4 bytes, But yeah, of course, you can actually be a bit more precise and say that maybe 3 bytes is enough or something, but that's the usual guess that 4 bytes is needed. Okay, any other questions? Those were very good questions, actually. Okay, so another operation, here I'm just providing some overview, but we're going to get to all this information actually later, is actually garbage collection. So since whenever you receive an update, you don't write to the same location. You just pick another free location and you write to that. So at some point, you're going to run out of all these free locations, right? And so you need to reclaim free pages. So that's the job for garbage collection, that you need to select. Basically, garbage collection selects a victim block, and then it needs to copy all valid pages to the free pages that you already have, and then you can erase the victim block to make another available free block. But we're going to see a lot. Weir leveling is also another important operation. As we discuss, these memories, they all have endurance problem. And if you keep write to the same location, your device will wear out quickly. So weir leveling is an important task to evenly distribute SPI cycles, program erase cycles, across NAND flash blocks. So that's why we need this weir leveling. And it's usually, there can be a lot of actually, implementation for weir leveling, but at the high level, most of the time they need to swap hot and cold like blocks. If there is a block which is hot, meaning that you write to that block a lot, and there are some blocks that they are cold, meaning that you haven't written to them much, you can just swap them, basically. And that's actually quite easy with flash memory implementation, because with SSD implementation, because you already have this mapping thing. You can just map things differently. If you just change the mapping, like the logical to physical mapping, you can actually also easily implement variability. But at the DRAM level, it's not easy, like the main memory, because you don't really have much of this logical to physical mapping. So that's why implementing like variability techniques for PCM PCM as the main memory is not that easy also. Another operation is data refresh, which not actually happening so frequently. You know that for DRAM, we need to refresh it very, very frequently because, it loses charge. But in flash memory also, we need to do that. We're going to learn about it more, actually, tomorrow. But at some point, you need to refresh pages with long retention ages, like, for example, every month or every year, depending on your technique. So there are some trade-off here. If you, for example, refresh your pages, your NAND flash pages every week, for example, you're going to cause some issues, like some energy efficiency. But at the same time, you can reduce the number of ECC, like you can reduce like error correction code capability, and that can can buy you some other benefits. So seriously, here also we have another trade-off. Okay, and for flash controller, you need to, so for rewrite, now you have your data and you send it to flash controller. So first, the flash controller tries to like scramble data to write. So there is some, let's say, key, and that flash controller in the randomizer unit scramble your data in order to avoid worst case data patterns. So there are some data patterns, like the data that you want to write, that people show that these patterns can cause a lot of reliability issues. From study that we will also show some of these studies tomorrow. When you deep dive into the flash memory, you can actually learn about what are the data patterns that they can cause more reliability issues. So these patterns can cause reliability issues as well as security issues. So once you know, some people malicious program, or they can use these patterns to cause reliability issues for your data. So that's why in flash controller, you just scramble your data with a key such that hopefully you can avoid worst case data patterns. So that's the job for randomizer. So the data that you write to your flash memory is actually different from data that you send to your device. And also you need to apply these error correcting codes, ECC, which can detect and correct errors. As an example, you need to keep 72 bits per 1 kilobyte error. 1 kilobyte of data for error correction capability, and that stores additional parity information together with your randomized data. So inside the flash memory, you write your randomized data as well as ECC parities, basically, essentially. And after that, you can issue NAND flash commands, like saying that I want to write to this NAND flash package. Any question? Yes. Yes. No, it's scrambled data, like data itself. That means when you want to read it, you need to de-randomize it. So basically, randomization algorithms should have that capability. I mean, usually it's just like chain of XOR that you do randomize, right? And then you de-randomize things. Say it again. Yes, yes, yes. Yeah, the question is that when you want to write a page to a block, you randomize the whole data of that page, right? Was that your question? Like modified, right? Yes. Yeah, you need to modify data using this randomization algorithms. Questions? Okay, good. So now that we are done with write, let's see what happened when we want to read. So the host system sends a read request. And then we, at the FTL, we need to first check if the request data exists in the write buffer. And we might be lucky, right? Which again is not a, let's say, frequent case, because most of the time you don't really have that locality. But it can be also the case that you find your data in that write buffer. So if that's the case, you just returns the corresponding request immediately with the data. And also a host read request can be involved with several pages. Like you can, when you send a read request to your storage, it can actually be asking for one page or can be also several pages. The host system will actually send acknowledge to the HIL layer, sends the acknowledgement to the host with the data once all the data is ready for that. But if your data is not ready in that cache, in that write buffer, you need to basically check address translation. Why? Because you know the logical address, but you don't know where your data has been stored. So you need to check this physical, like the logical physical mapping. And then with in order to get the physical page address, this PPA stands for physical page address. In order to get that physical page address, we need to access the logical to physical mapping table. So once you know, then you can just send the read command to that corresponding NAND flash page. After getting your data from NAND flash page, you need to perform ECC decoding. And if things are okay, you should de-randomize the raw data such that you have your data ready, and then you can send it back to the system. There might be cases that ECC decoding failed, which is actually quite frequent, especially when your device is aged. So you're gonna see a lot of these ECC fail. And then the flash controller needs to retry reading. So hopefully, by retrying, we need to adjust the reference voltage. We're gonna learn about what is reference voltage, but essentially we showed like how PCM works, right? PCM was like the distribution of the resistance. And we show that we can chop the distribution of the resistors in order to get, what's the data has been stored. So in flash memory also, you have a distribution of threshold voltage, and you can chop that window into several domains or several margins. So essentially, you need to send a reference voltage, and then with that reference voltage, you can decide if your data is 0 or 1 or whatever. So once things are failed, you need to adjust that reference voltage. You reduce it or increase it, essentially, and then you need to retry. So that's actually one of the reasons that aged devices are quite slow. You might need to actually do several reads in order to get one read data. Yes. 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 Exactly. Flash controller does that, yeah. So if that happened, repeat the, yeah, the question is about, after all, do you get your data correct or not? After all these retry that you did, that you do, yes, that's possible. But if that happened, then your system is basically, I don't know, you may get some blue screen. I'm kidding, but basically your device is not working well. So the goal for a storage device is that with all these retries and all these ECC, you're gonna get your data. But there are also some studies that I'm gonna show tomorrow that we have done larger scale studies in the widespread of, like, at the server domain, at the software level. So at the software, you can actually get those errors, those failing things, and you can say that, this device is not working. And like, for example, Facebook, for example, reports that, some of my SSD, some of my storage devices are not working. And then you can, get some idea about it. But at that level, meaning that all these ECC stuff, retried, they didn't really work. So most of the time you don't really get, you don't get into all these errors because storage subsystem fix things. At the another level is also RAID controller. You have actually several storage devices. You can have them in RAID, and RAID actually can also provide some other parity. So at the software level, you try also to get rid of many errors, but at some point, your device can just get you wrong data. Okay. So now we can actually get into more detail. We are done with the overview. So let's see what is flash cell. So flash cell is basically a transistor. Like that each transistor, we have this source, drain, and gate. And depending on the voltage that you provide between gate and source, if it's larger than threshold voltage, your transistor will be on, and the other way around is off, basically. So you can assume it as a key switch. But the difference with flash cell is that we have a special material called floating gate in 2D flash cell, or charge trap in 3D structure of that flash memory. That here I'm showing the 2D version, the floating gate. So this is the special material that you have. And this material can hold electrons in a non-volatile manner. So essentially, when you want to program it, you need to apply a high program voltage, like 20 volt. And this positive voltage will basically absorb electrons, like calling tunneling, to this floating gate. And when you basically switch off that voltage, or when you cut that voltage, these electrons will be trapped here, so they don't get back to the substrate. In order to get back to the substrate, you need to actually apply a negative voltage, like minus 20 volt, to push all these electrons back to the substrate. And that's the operation for erasing flash memory. But once you program it, you need to apply the positive voltage such that you can get electrons to the floating gate. And since you have a positive, you have a negative. So once you have electrons here, now you have a negative charge here. That means you need to provide a higher gate source voltage in order to turn on that transistor. Meaning that your threshold voltage now is higher. So once you program your flash cell, you have a higher threshold voltage. Clear? Yes. So when you want to erase it, you need to apply, for example, minus 20 volts. Yeah, it's not that easy, and that's also part of the reason that's why flash memory, this program erase doesn't really work well, because once you erase it, there are some electrons that they will remain. Actually, it's not the perfect process. When you again program it, you add more electrons, and then because of the previous electrons, now you have more negative charge. When you again erase it, so this is not a perfect basically process. And that's why with several of these program arrays, at some point your flash memory is dead, essentially. You cannot use it reliably. Question? Sometimes I forgot to repeat questions, but yes, it's one of the main reasons of endurance problem in the flash memory, is that your program erase process is not perfect. So every time you do, you leave some electrons, or you may actually you have less electrons. If you apply that positive charge longer than needed, you may actually cause more electrons to move to substrate, and then you have a positive charge in your threshold, in your gate. Okay. Yes.
So while we are reading,
yes. Yes, exactly. So when you want to read, you just apply reference voltage, and that reference voltage is something between your two threshold voltage. This one is the nominal threshold voltage, and this one is the programmed threshold voltage, which is higher. So you need to apply this reference voltage. If your flash memory turns on with the reference voltage that you apply, it means that you haven't programmed, and you can decode it as 1. You can encode this state as 1. And if your flash memory doesn't turn on, that means that you have already programmed it, and you can encode it as 0, for example. And this is, of course, the SLC mode. You have 1 and 0, but it can be also MLC that we're going to also see more. Any question about the basic operation of flash memory? Good. So in order to erase it, you need to apply negative voltage, like minus 20 volt, and that can tunnel electrons back to the substrate. And hopefully you can get your nominal threshold voltage. Okay, so let's see some of the flash cell characteristics. First of all, you can actually have this multi-leveling. A flash cell can store multiple bits. So when you program, you inject electrons, and when you erase, you eject electrons. You can actually, control it more accurately, and you consider that you have 4 levels in the threshold voltage, and then you can encode it to 2 bits. It can be also 8 steps or 16. So we even have QLC flash memory now in the market as well. We have retention loss, same as DRAM, but it's not as fast as DRAM. So a cell leaks electrons over time. Like after, this is the initial step, let's say, initial state. And after 1 year, you have some, loss. And after another year, you have more loss. And at some point, you can get retention error, essentially. The thing is that this P cycle, like the program race, can actually cause limited lifetime. And it can actually makes this retention error worse. Like, for example, if this is the initial state, after 1 year, assuming that you have around 1,000 PE cycles, you can get this charge level, meaning that you can read from flash memory correctly. But the same thing, after 1 year, with 10K PE cycles, you can get to this. So basically, PE cycle can accelerate how fast your flash memory lose charge. Yes. Program erase. So whenever, we do program and erase, like injecting electron and ejecting electrons. Question? Okay. So this is flash cell, and we have NAND string, like these multiple flash cells. Example can be 128. There are also other numbers depending on the product. So these multiple flash cells are serially connected in a NAND string. You can see that we serially connect all these flash cells in a NAND string, and then this NAND string is connected to a bit line, essentially. Assuming that this cell is your target cell, when you want to read it, for example, you should apply reference voltage to your target cell. And in order to make sure that other cells do not interfere with your process, like read or write, you need to apply the high enough voltage, which we call it VPass, meaning that this voltage is high enough to make them on, no matter you have programmed them or not, essentially. So here, for example, is like around 6 volts. Tomorrow, we're going to learn about this VPass, VPass is actually quite high, and that can cause some weak programming effect. So when you want to program your flash memory, you need to actually apply high voltage, which is actually quite higher than 6 volts, as I showed, like it's around 20 volts. But even 6 volts can also have caused some weak programming issue. And that weak programming can cause some reliability overhead to the flash memory. But wait for tomorrow for that. So then when we combine all these NAND string, having them in a row, very, very similar to how we struct DRAM row, we call it a page. Like you can also see the similar terminology here, like the word line, right? And the whole thing, like basically all these bit lines and then the string, we call it a block. And essentially block is like the number of word lines that we consider times number of bits per cell, like because each of these each of these cells can be SLC or MLC, right? So when we want to see how many pages each block can store, you should also consider if your cell is SLC or MLC. Assuming that we have SLC, each word line stores 1 page. And this alpha here is actually those metadata, like the ECC and some other stuff. So like page is 16 kilobyte, and you need to store it. And in addition, you need to also keep some more data. So that's the word line. And you can see the number of pages that you can have in a block. Yes. Per block. So these pages and block program arrays, as you can also imagine, is unidirectional, meaning that when you program a cell, you increase the cell threshold voltage. And when you want to decrease the cell threshold voltage, you need to raise the cell. So you cannot program, like there is not such a process that you increase threshold voltage in a program and also reduce threshold voltage in a program. You need to erase it. And that's a completely different process. Like, it's a completely different process because you need to apply negative voltage. And at the same time, you need to do it at a higher granularity. And the reason is that erase process is actually quite slow. In order to at least provide good bandwidths, you do it at the block level. For program, you can actually do at the page level. So read and program actually happening at the page level, but raising is happening at the block level. And we know that when we want to program a page, that cannot change 0 cells to 1 cells. So that's why you need to erase it before write. And that's one of the big issues that we have in flash memory. And as I said, erase unit is at the block, and you can, and in order to increase erase bandwidth, and that makes in-place write on a page very inefficient. So once you want to do, like assuming that you want to do in-place write, like in-place update, what you need to do, like there are some pages in that block. You want to update 1 page, right? So the problem is that you cannot update. First, you need to erase that page, right? You need to erase that page in order to write to that page. The problem is that when you want to erase that page, you need to erase other page, the whole pages that you have in that block. Like the whole block needs to be erased because the erase granularity is that block. So before doing that, you need to copy all the valid pages that you have in that block to somewhere, like in DRAM, let's say, and then you can erase that block. Once the whole block is erased, then you can actually program. And not only that page, you need to program other pages that you have also copied them. Now you can see, for every write, how much time you need to spend in order to have in-place update. So that's why in flash memory, we just do out-of-place update. So hopefully, we're going to keep enough number of free pages that whenever you receive an update, you just write to another. And that also caused some other issues, like, as I said, garbage collection. We're going to see that at some point, you're going to run out of these free pages, and you need to reclaim them. But I just wanted to give you some insight about why we need to do out-of-place writes. Okay, so, and playing is a large number of blocks. Yes. So normally in QLC, when you want to, when you write, you actually write to the whole page. Like in QLC, you can consider that each word line stores 4 pages. And that's why you actually need to have data for the whole pages, and then you can program QLC. So you don't really program only one, basically, bit of that QLC. Is that correct, Rakesh? Like for QLC, we need to program 4 pages at the same time, right? We don't really, yeah. No, but that's the operation for write buffer, essentially. Yes, you need to, for write buffer, no matter if it is DRAM or SLC, you need to first write to that in order to keep things, like you need to have 4 pages. So you write to that SLC, and then whenever you have 4 pages ready, then you write. So that's the process. We're gonna get back to that actually when we want to discuss about fine-grained mapping actually. Okay, so a large number of blocks share bit line in a plane, like more than 1,000 blocks. You can see that all these blocks, they are sharing the same like bit lines. So then the question is that how we can control each block to access bit line, and that with some transistors like isolation transistor that you have seen it a lot for DRAM works that we have done. Like here also we have these 2 transistors like a string select line and that we need to add per block. And when one NAND string wants to connect to that bit line, you need to actually turn on these 2 transistors. And that's the way you can control which block is controlling the bit line, essentially. And that's the definition of plane. And in flash die, we have multiple planes usually. And the thing is that these planes, they are sharing row and column decoders. And that's why you can actually do parallel operation across planes, as long as the offset and also the operation is the same. Assuming that you want to do the same operation, like the read across planes, and all these read operations are consistent in terms of the offset, you can do it in parallel, essentially. And that's actually caused a lot of also control, like also trade-off that we're going to see, that how we can benefit from multi-plane operations, because multi-plane operations provide better bandwidths for you. But at the same time, it's also quite hard to keep it always. Any questions? So if you want to make it, like, question is that how likely we can get multi-plane operations. If you want to make it more likely, you need to control it. When you want to write, and when you want to do write operation and at the garbage collection, you actually need to dictate multi-plane operations. So that's we're gonna see, and that's one of the reasons that brings us to the trade-off. Sometimes dictating multi-plane operations can cause some other overheads, and you need to do it intelligently, which is not also easy to do it intelligently. Exactly. When you want to control that write operation, you need to make sure that these planes are filling up the same. So when you want to pick up with the victim block, these victim blocks should be aligned such that you can erase them together. There are a couple of stuff going on there. Okay, so as we discussed, we have this threshold voltage distribution in NAND flash memory. Here I'm showing the SLC, like the nominal reference voltage, nominal threshold voltage we consider as erased and 1. And this is the program reference voltage. And of course, we have this distribution, so things are not perfect because of the process variation. So there are some cells that they are like more easily programmed or erased, so that's why we get to some distribution here. And this is the way that we can also get to multi-level cell. Like in order to have m bits per cell, we need to keep 2 to the power m threshold voltage. Here we are showing 8 basically regions. And with that, you can encode 3 bits, like LSB, CSB, and MSB, meaning that you can store like 3 pages in your word line. So as you can see, we have limited widths here now for the threshold window. And that basically make each threshold state narrower. So you have narrow, and this margin is actually quite lower. So that's why we have reliability issues here. That threshold voltage changes over time. So after some time, actually, these threshold window are moving across this basically axis. It's also not always reducing. You're gonna also see tomorrow that they may actually shift it to the right. It's not only shifted to the left. And it's also not the fact that it's shifted, it's also widened after some program. So it's also getting widened. So at some point you can see that these regions, like here, they conflict to each other. So then when you apply, there is no way to avoid error. So when you apply this reference voltage actually between these, you may get some errors essentially. And hopefully you can fix those errors with ECC. But that's why actually ECC is needed. Even though you can actually apply a lot of techniques in order to reduce the requirement of ECC, but you cannot really get rid of ECC completely, because there can be also in the end some, some collision that you need to apply ECC. Question? Whenever I think about such things and I read, I'm always amazed how our system is working essentially. With all these error sources, it's really incredible, right? You just copy data in your flash memory, your SSD, and you never think about such errors. It's quite interesting. Okay. So let's get to some basic operation like page program. We discussed about like the read operation at the system level, at the storage, but now we want to see how we can do like read and write. We want to see how we can program at the flash memory level, assuming that now your data is sent to the flash memory and the controller asks flash memory to write, like sending the write command. So you have a target page, assuming here we have SLC. You have a target page and you want to program this. You need to apply essentially for those SSL and GSL, you need to activate them, like those isolation transistors. And other word lines, because they are not related to your work, you need to apply VPass, which is high enough to make them on, essentially. And for the target page, you need to apply program voltage. So then we have an interesting control here that we can control bit lines. So when you want to program, you know that the whole page should be erased, meaning that all cells are considered as one, basically, So all of them are now, they are storing one. So the data that you want to store, some of them, you want to make them 0, some still need to be 1. So you don't need to program. So if you just apply program, you're going to make everything 0. But that's not what you want, right? You want to control which cell you want to program in, which cell you don't want to program in. And that's a very interesting, basically, mechanism here that we can inhibit cells to not be programmed. And that's by applying VCC to the bit line. So those bit lines that you connect them to the ground, you can program them. But those bit lines that you don't want to program, like those cells that you don't want to program them, you apply VCC to the bit line and you inhibit those cells. And essentially, your program voltage does not affect them. Okay? So you have this is the distribution of your threshold voltage before programming. And once you program, you hopefully get to this basically distribution that some of the cells are programmed, the other cells are not programmed, depending on your data pattern that you had. But unfortunately, if you apply the program voltage at once, like that 20 volt, you will get to this kind of distribution. That's essentially the cells that you want to program, the distribution is just scattered, through the whole window, which can show, essentially your program is not successful here. And the reason is that, as I said, we have process variation. There are some cells that they are hard to program. Like, as you can see, their threshold voltage, doesn't change much. There are also some cells that they are easy to program. So the threshold voltage for them changes well. So that's why this doesn't work. In order to overcome this issue, people come up with this interesting technique that they call it incremental step pulse programming, ISPP. And that's, you apply program voltage step by step. You first apply a program voltage, which is less than the high program voltage that you need. So with that step, some cells will be programmed. You get to this after applying V program 0. So you can actually verify. You verify by reading from your flash memory and see what are the cells that they are programmed already. For the second cycle, you just inhibit them. Like this, for example, is verify as program. You just need to inhibit it. So you apply VCC to the bit line such that for the second cycle of program, you don't affect this cell anymore. And then you need to apply program 1, V program 1, V program 2, and at some point you get to this beautiful distribution. So that's the process of ISBP, very briefly. Of course, there are many also other details that I'm not gonna say now, but you get the whole idea, I guess. Any question? Interesting? Good. So now let's see how we can read. So for read, things are a bit easier, I hope. So in SLC mode, you need to apply reference voltage. And for bit line control, you need to charge all bit lines to VCC. We're going to learn about sensing circuitry actually today. But you need to initialize, essentially, like the pre-charge. Like then terminologies are similar also to DRAM because both of them are charge memories, essentially. So you need to pre-charge and pre-charge the bit line to the VCC. And then you apply VREF. So if the reference voltage does not turn on your transistor or your flash cell, meaning that you have programmed it, so the current doesn't flow, right? And you can encode it as 0. But if the bit line current flows well, you encode it as 1. The way that we understand that if bit line current does flow or does not is from a sensing circuitry that we're going to learn. But the process is very similar. Like it's quite easy. So if bit line current flows well, meaning that this switch is on. Like when the switch is on, bit line current will flow. That means that in this example, that means that you haven't programmed this flash cell. But if the bit line current doesn't flow, that means that you have programmed that flash cell and you encode it as 0. Is that clear? Okay, good. So now let's see how we can read in MNC, basic this cell. So assuming that we have a TLC here, which, I mean, the whole is called MLC, multiple level cell, but this example is actually TLC, which is triple level cell, which you have essentially 3 bits per cell. So if you can check, you can see that in this window, like the threshold distribution, you have 7 reference voltages, which means you need to apply multiple reference voltage in order to get your data. But do we need to apply 7 reference voltage, for example, in order to read the CSP bit example here? Any thoughts? Like how many reference voltage I have to apply in order to correctly read the CSP? 3. And why is that? Say it again. And what are these 3 reference voltages? VREF 3 and VREF 1 is also correct, but VREF 0 no. You need to check for the reference voltages and VREF 5, yes. You need to check for the reference voltages that you see toggling, essentially, in the encoding. So here you can see that we have toggling from P1 to P2, like for the CSP. 1 gets to 0, meaning that VREF 1 is something important for me because that shows some toggling. VREF 0 is also important because you see a toggle 0 to 1, and VREF 5 is also important. Other reference voltage are not important for reading CSP. How about LSP? How many reference voltages I need to apply? 2. And what are they? Yes, correct. Okay, so for reading CSP, you apply these 3 reference voltages, and you read. So first you apply VREF 5, and here are the data that you read. You can see that for some of them you read it correctly, like this one is correct, this one is correct. but this one is incorrect. And the reason is that VREF5 was not enough in order to read that CSP. Then you need to apply also reference 3. You learn, you read it from them. And then VREF1. Finally, you get the correct data for that. So with this kind of encoding, you need to, so you have output from each of these read process. You need to somehow combine these outputs to get the final output. So with this specific encoding, you can actually get that output with XORing. You can check at home as a homework if you are interested, but essentially XORing these outputs, you can get the final correct values in this example. Yes. Say it again. So you only so every time is actually, when you want to read from MLC flash, essentially you are doing SLC read every time. But that's a reference voltage that you apply, right? But every time is SLC read. So you are doing SLC read 3 times here, and then combine. So that's why actually MLC NAND flash memory requires an on-chip XOR logic. And we actually have used that kind of XOR logic in order to do computation as well in one of our work, MQ Flash Cosmos, that we're gonna also present it sometime. And you can see that bit encoding affects the read latency. So now we have this CSP, for example, we have 3 reference voltage, like 3 reads process. For LSP, we observe that we need 2, and for MSP, something else. So let's compare these 2 encoding, for example. The first one is exactly the same that I showed in the previous slide, and the bottom one is completely different. So compare the number of sensing for LSP. How many sensing I need for the top? You already answered it, actually, 2. So we need 2 sensing for the top. But for the bottom, we need to do how many? 4. Exactly. So this encoding needs 4 sensing for reading LSP, for example, page. But now let's compare MSP. So for MSP, the top one, you need to do 2 reference, but the bottom is a good one. Like you need to only apply 1 reference voltage. So now you can see the trade-off for encoding. And people have done research on it, like how to benefit from that intelligently, like make the MSP page as the cache for the LSP page, for example, because MSP page is faster, to read. So you can consider that MSP pages are cache or pages that they are more latency sensitive. So if you have information of your application and you know that what other pages are more latency sensitive, you can map them to the MSP, assuming you have this encoding. So yeah, you can assume that people have done a lot of research. And what is the exact encoding we use in our product today? We don't know. And and each industry can have its own actually encoding. So we don't really know. I mean, Rakesh can share some information and then you cannot see Rakesh anymore. Okay. Okay, let's take a break, I guess. Now we are in a good position until 2:30. Then we can continue from this. Okay, let's get it started. So now I want to give you a little bit more information about how the sensing circuitry in the flash memory works. Like NAND flash read mechanism consists of 3 steps: pre-charge, evaluation, and discharge. So in pre-charge, you need to pre-charge the bit line to the VCC, and there is also a transistor here that connects the the bit lines to the pre-charge voltage. So you need to do that in order to get bit line to that pre-charge level. And it's here also we have a capacitor, assuming. So now you charge this capacitor CSO to high voltage. In the evaluation, basically you apply reference voltage. You also need to turn off this pre-charge transistor. You apply reference voltage to your flash cell, and then you observe that this bit line current flows or not, essentially. If it flows, like we know that this is erased, so you code it as 1 and the other way around. And after that, for the discharge, essentially you need to make sure that bit line gets completely discharged. So that's the process for discharge. But now the interesting part is actually latching circuitry. So how you really sense that the current is flowing or not. So you can see this simplified version of it. Like this is your bit line. We haven't shown the NAND string anymore here. So we have a bit line. And this is a pre-charge voltage. And this is transistor pre. Here is also that capacitor that you charge it in the pre-charge mode. And this is actually essentially your sensing circuitry. You can see you have this back-to-back NOT, and all the 2 sides is actually connected to this transistor using 2 separate transistors, M1 and M2. So let's walk through it quickly, together. It's actually quite easy. It's not a magic, but it looks a bit complicated, essentially. So when you want to initialize, like that, the pre-charge mode, you activate this transistor and you charge this SO to 1, essentially. So now you have high voltage here. When you have high voltage here, this transistor is also on, right? So now you have a connection to the ground. And for these 2 transistors, M1 and M2, you basically activate only transistor M1, and M2 is off. So since you apply M1, this out bar or out prime is also connected to the ground, because this part is connected. So now you have a connection to the ground. That means your voltage for the out prime is 0. And because of this back-to-back NOT, you have V out set to 1. And this actually remains to 1 because M2 is not connected to the ground. Clear? So that's the initialization part. Any guess? How can we evaluate it? For the evaluation step, you need to disable this pre-charge transistor. And then also M1, you need to disable M1 and then activate M2. Correct? So now let's see what happens, essentially. When you deactivate this pre-charge, assuming that also you have applied reference voltage to that transistor. So we have charged this SO to 1, right? And this one was controlling this transistor. If the current flows, then this SO will go to 0, meaning that the connection of this transistor to ground will be basically disconnected, right? So you don't really have connection anymore to the ground. And that's why actually turning on M2 doesn't really, does not do anything, essentially, because there is no connection to ground. And then all these out prime and out will keep their voltage. And you can see that you are reading 1. So And that's what you should have read as well, because the current flows. So now you're reading one. But if the current doesn't flow, this SO will keep its voltage, meaning that this connection to ground is still there. So when you apply M2, then you have a connection to ground, and V out will go to 0. And then out prime is also goes to 1. And now you're reading 0. So simple, right? It's not a magic, honestly. Okay. Any question? Interestingly, this process has a characteristic. If you just swap M1 and M2, you can do inverse read. So in the pre-charge, in the initialization mode, if you activate transistor M2 instead of M1, and in the evaluation, you disable M2 and enable M1, then you can actually read inverse, meaning that you can implement easily NOT operation inside the flash memory. So you store 1, but you read 0. So that's a NOT operation, essentially. You can do it on your own at home. Okay, now that you know about the process of read and program, as well as also this sensing circuitry, now let's also do some performance evaluation. But we'd like to know, what are the performance of the SSD, essentially. So in order to evaluate performance, we have different metrics for SSDs. One of them is latency or response time, which is the time delay until the request is returned. So the average read latency for 4 kilobytes of page is around 67 microseconds. This is actually data coming from this SSD. It's one of the high-end Samsung SSDs, actually. And average write latency is around 47 microseconds, which you can see that actually write is faster than read. And the reason is that you are writing to the right buffer. If you have to write to the flash memory, then you're gonna see that the average latency is around actually like hundreds of microseconds. Another metric is throughput, which is the number of requests that can be serviced per unit time. So in the throughput, we consider the number of requests, and we don't really care about request size, essentially. So that's there's a metric for that, which we call it IOPS, input output operation per second. And it's actually has been used a lot for random accesses. Like for random read throughput, we know that it's up to 500K IOPS for this SSD. And for random write throughput is up to 480K IOPS, essentially. And bandwidth is the amount of data that can be accessed per unit time. Here, you actually care about your size because you're calculating amount of data. And that's the bandwidth for sequential read up to 3,500 megabytes per second. And for write bandwidth is up to 3,100 megabytes per second. And if you compare them with HDD latencies and performance, for hard disk drive, a latency is around 5 to 8 milliseconds. So you can see why SSDs are everywhere, essentially, for better performance. Throughput for HDD is around 1,000 IOPS. And the bandwidth is also around 100 megabytes per second. So essentially, we observe around 2 orders of magnitude improvement when you go from HDD to SSD. So for the NAND flash chip performance, we have this chip operation latency, and there are a couple of parameters here that we consider here in order to evaluate the performance. One of them is TR, which is the sensing latency, the latency of reading data from the cells into the on-chip page buffer. So per flash chip, we have some buffer again, like very similar to DRAM, that we have this row buffer. Here also we have on-chip page buffer, and the latency that you need to spend in order to sense your data, to understand it is 1 or 0, and put that data to that page buffer, we call it TR. We also have T program, the latency of programming the cell with the data in the page buffer. Assuming that your data is ready in the page buffer of that flash memory, then you need to spend T program in order to have your data written in that or program in that flash memory. And also TBER, which is latency of erasing the cell, or which is happening actually at the block level. So these all values are depending on the MLC technology, processing node, and microarchitecture. In the 3D TLC NAND flash memory, which is again the same device as I showed in the previous slide, TR is around 100 microsecond, T program is around 700 microsecond, and TBR is around 3 milliseconds. Another important metric is I/O rate, which is number of bits transferred via a single I/O pin per unit time. So flash memories, currently they have 8 I/O pins, like for data, and these each flash memory is connected to the channel, and that channel is also 8-bit wide. So essentially, you can and each single I/O pin has a I/O rate of 1 gigabit, meaning that for basically in order to transfer 16 kilobytes of page, since you have 8 I/O pins, the whole bandwidth you have is around 1 gigabyte per second, right? So transferring 16 kilobyte page to the controller will cost around 16 microseconds. Just simple math here. Okay. So now let's do some calculation. So we know that these are the values for the sensing, programming, and erasing. Like you can see also some range here, because I mean read can be 50 to 100 microsecond average, and program can be also 700 to 1 millisecond, and erasing is also varies. I mean 3 millisecond to 5 milliseconds. So for the operation, like for the read operation, these are the operations that you need to do. So flash controller needs to send a command to the NAND flash chip, and then you need to spend the sensing time, TR, and then you need to communicate that data that you have read to the controller, TDMA, and then you need to do this ECC decoding and as well as randomization. So these are the values that we assume. For command, we can assume that this is actually negligible, so we don't really count it here. For sensing is around 100 microsecond, TDMA is 16. ECC decoding is also around 20 microsecond in this example, and then you can see that your read is around 130 microsecond. Yes. Retry. It's actually quite likely, especially when your device is aged. Yes. There is actually a very nice report that I will show tomorrow, that people show that SSD device that they bought, like, I don't know, some years ago, and it was supposed to provide, let's say, X amount of bandwidth, for example. They test the bandwidth after some years, and they see that it's actually like several, I'm not really sure about the number, I will show tomorrow, but they actually observe dramatic performance drop of that SSD. So when you use your computer for some time and you see that it's getting slower, that actually might be one of the reasons. There can be many other reasons as well, but SSD also gets slower as you go use it. Okay. So this is some amount, for read operation. Yes. Yes, yeah, exactly. Yeah. No, so this metric is fine-grained, right? It's a TR is sensing time, or TDMA, for example, is per page read. If you need to retry it, you need to multiply TR and TDMA, essentially. You need to do it. Yeah, exactly. But in this example, we consider that things are beautiful. You don't need to retry it. Okay, so these are the operations that we already talked. And for program, essentially, you need to do something similar. You first do randomization, ECC, then you send the command, transfer data to your NAND flash chip, and then you program. And you can also do some calculation and get some numbers here for writes. Yes. Yes. Yes, yes. When you send program command, you need to actually send program command to pre-erased block, essentially. Pre-erased pages. Yes, that page needs to be erased. The whole block is erased before, but at some point you program some of the pages in that block, right? But the page that you want to write to it should be erased, should be pre-erased, essentially. Yeah. You erase the whole block, but when you want to write to that block, you don't need that all pages in that block should be erased, because as you go to the future, some pages are programmed, essentially, right? Okay, so you see some numbers here. And if you calculate the bandwidth based on these numbers, you can get to these low bandwidth, essentially. And if you compare about the read latency, read bandwidth, write latency, write bandwidth that we have shown, you can see that there is huge difference, essentially. And the reason is that there are many optimizations and advanced commands that SSD has been applying. So first of all, we have internal parallelism. And also we have write buffer of DRAM and SSD. So you can actually accelerate things with write buffers. And there are also other optimizations that we're going to show a little bit today. But with this internal parallelism, for example, you can actually send several reads at the same time. So your average latency will be reduced. Even though for each read, you may spend like 100 microseconds. But if you do that for several reads at the same time, then you can think of much lower average latency, right? So now I want to start and very quickly talk about some of these optimizations. So one of them is what we do for small reads. Like the minimum I/O units in modern file system is 4 kilobytes. But page size in most of the SSDs today, like capacity optimized or cost optimized SSDs, are 16 kilobytes. There are some SSDs that they are performance optimized and they are using lower pages. But usually the SSDs that you can use, they have larger page sizes, like 16 kilobytes. So if the host sends a request for accessing 4 kilobytes, now you have this mismatch, I/O unit mismatch. So when you read from your flash memory, you read 16 kilobytes, but you only need 4 kilobytes. So that's a problem, right? So there are two optimizations that people have developed. One of them is sub-page sensing. Is actually a prototype from Micron that they did some microarchitectural level optimization that you can directly reduce TR. When you want to sense 4 kilobytes, you really spend also less time. You don't really need to spend like 50 microseconds in order to sense 4 kilobytes. You need to spend that time if you want to sense 16 kilobytes. So there is actually some microarchitectural implementation. If you're curious, you can check this reference to learn more, but you can also get some idea about it. Another optimization is random data out. So you sense, let's say you can read 16 kilobytes, but you have that in the page buffer, on-chip buffer that you have in your flash memory. Then you don't need to spend the whole time, like the whole 16 kilobytes to send it back to the flash controller. You only random data out. You only send out the data that you want, 4 kilobytes, for example. And that can be in any offset, essentially. So this can reduce TDMA and also the ECC decoding. So you only spend DMA and ECC decoding for data that you care about, essentially. Yeah, these are two optimizations, for example, for handling minimum I/O units in modern file systems. Another interesting command is cache read. It's actually quite good for consecutive reads in a pipeline manner. So this is a process for read A, page A, for example. You need to spend TR and then TDMA and TECC. Then you can wait for some time, and then for the second read, you need to actually wait until TR and TDMA is done. And then from this time, because your channel is now free. Once the channel is free, you can start doing send the NAND, send the read command to that flash memory, and then start this TR and TDMA and TECC. So you can see that in regular page read, you can overlap TECC with some of these sensing time, essentially. So that's good, but we want to do better. And that's happening with the command cache read. So when you send a read operation, you also send the read read operation of page A. You also send the read operation of page B as a cache command. Like you are telling flash memory that you first need to provide me the page A, but immediately after that, I also need you to provide me page B. And with that, you can see that you can overlap TDMA and TECC. Like, how is it possible? You are sending these two commands together. So while you are doing the read of page A, you are doing sensing and then move page A to the page buffer. Then together with data out of page A, which is TDMA, you can also start reading page B. Like you start sensing of page B. And with that, you can overlap sensing of page B with the TDMA and the ECC of the previous page. So that's the cache command, essentially. Any question? But of course, it doesn't come, with no overhead. You need to apply, you need to have more, let's say, buffers here. So now you need 2 page buffers here. So it comes at price of some, overheads, essentially. Okay, so this removing TDMA from the critical path, it increases throughput and bandwidth, and it reduces effective latency, as we discussed. It doesn't really reduce latency for every command or every request, but overall, since you have higher bandwidth, then your effective latency is lower, and you can use it. But as I said, it doesn't come free, and you need to add more buffers. Another optimization is multi-plane operations that we also briefly talked about it before. I'm gonna skip it very soon, actually. So we have this target page. As long as your target page in different planes are aligned, you can actually access them, simultaneously, and that gives you much better bandwidth, essentially. So you can actually overlap sensing time of all these pages together. Yes. Yes. Yeah. So I'm trying to find a simple answer to that. Yeah, essentially, you need to. So one of the way was, you need to come up with the big accesses, like large accesses, like several accesses together, and you send them sequentially, as a big request to the SSD. But there might be some other, more detail to that, which I cannot remember from top of my. No, you need to do it for the whole SSD, actually, if you want to get the bandwidth across the channels. One of the good reasons for that sequential read is actually you can scatter it across channels, and you are benefiting from multi-channel parallelism. So you have channel level parallelism, you have page, you have also die level parallelism, and you have also plane level parallelism. If you want to get the maximum throughput, you need to benefit from it. And there might be there needs some reverse engineering about how the access pattern, like how FTL maps things, With that, you can come up with the access pattern. There are papers for that, but Rakesh, do you have anything to add? You want to use? Turn it on.
Usually, when the application requests for more than 64 kilobytes at a time, then you consider it as a sequential request. And then, so the application sends the request to the SSD, and then you make it into sub requests, and then process it through the FTL. So that's what we consider as sequential requests. But for random, you usually have 4 kilobytes, very small requests. Thanks.
Thank you, Rakesh. Okay, so yeah, this is a multi-plane. As long as I said, like the offset is the same, you can use it, and you can concurrently operate. So with multiplane operations, of course, as I said, you can overlap sensing and program latency. I mean, depending on you're doing multiplane read or write. Essentially, you don't need to, for example, here is an example for a program. So previously you had to program like 16 kilobyte at the same time, and you need to spend like 732 microsecond, let's say, with those calculations. So you get to bandwidth of 22 megabyte per second, for example. But here, now you need to program 32 kilobyte because you want to do multiplane operation, assuming you have two planes here. So this 32 kilobyte, the latency that you need to spend. So you can completely overlap the program latency, which is 700 microsecond. But you need to, the other things you need to add to it. Like you need to spend twice TDMA and twice TSCC. So that's why here is a bit, like the formula here is a bit complicated, but essentially like 732 is the program latency plus 1 TDMA and 1 TSCC. So you need to also add another TDMA and another TSCC to it. But since you're really bottlenecked by the program latency, you get quite high throughput, like almost twice throughput when you get to these multiplane operations. So you can see that per operation latency increases because now you need to transfer more data. So like with regular page program, you have this ECC encoding plus TDMA and T program, but now you have to spend like this, like number of planes times encoding, ECC encoding plus TDMA. And that makes things longer. But the good thing is that for the program latency, you're overlapping things. And your average latency is reduced a lot. Any question? But how to ensure multiplane operation, we're going to learn about FTL's data placement later today. Yes. Why do we need that? No. This 732 is actually one program latency plus 1 TDMA and 1 ECC. So since you're doing multiplane operation, you need to add another TDMA and another TSCC, assuming that you have two planes. This formula is actually quite complicated. I mean, it's a bit misleading, honestly. But you can, let me decode it. So instead of having 736 here, you can consider that you have 700 plus twice TDMA, twice TSCC. Is that correct now? Yes. Or yes. Is that clear now? No, TDMA cannot be parallelized because you have shared channel. You know, you have 8 IO pins, let's say, like the channel. So you need to send it serially. You cannot. I mean, there might be also some innovation for that you encode your signal and send multiple signals on one link, but those can make things even more complicated. I mean, there has been research, assuming like if you know about information theory, you know that they are using the same shared channel for sending a lot of requests. Like they code it like TD. What's that? Yes, time division multiplex. Exactly. You can also do that in SSD, but it's also not that easy. Okay. Another important actually optimization is about what we do for program and arrays. So read performance is often more important because reads are on critical paths usually. And also writes can be done in an asynchronous manner using buffers, as we discussed. So now the problem is that we have significant latency asymmetry. For reads is 100 microsecond, for program is around 700, and arrays is around 5 milliseconds, for example. So if the chip is designed to program all the pages in the same word line at once, like the same thing that we discussed in the past, like when we have TLC, we want to program all 3 pages at the same time. You need to actually, this program latency is around 2,100 microseconds. So you can see that the worst case chip level read latency can be 50 times longer than the base case latency. If you are unlucky and your read latency is queued after program, let's say, or raised, you need to really wait a lot, right? So that's what we don't like. In order to fix this issue, people come up with the suspension technique. So essentially, we suspend an ongoing program or erase operation once a read arrives. Here is an example. You have a program operation going on, and you need to spend like 700 microseconds, and then you have this read operation for which coming here, but you cannot start read because your chip is doing read, chip is doing program. So then the latency for the average latency here, for program latency, you spend like 700. For read also, you spend like 700 microseconds, even though you could have done read in 100 microseconds. What you can do is you are doing program, and then you suspend your program and immediately service read. And once read is done, we do the program. Now you can see that the program latency is increased actually to 800 microseconds, but the read latency is still around 100 microseconds. So you can clearly see the improvement in the average latency, right? And the improvement is even more because reads are on the critical path of the system usually. So it has pros, like significant decreases the read latency, but it has cons as well, like additional page buffer for data to program. So now you need to add another page buffer. And this complicated I/O scheduling. Until when can we suspend ongoing program requests? Which I will also show something at the end of this lecture. Like you cannot really suspend or basically, yeah, exactly, suspend program all the time. At some point, your program needs to be done, essentially. So there should be some intelligent control on that, to realize until when we can suspend it. And also it has negative impact on the endurance, which is also another issue. Whenever you do this suspend and you repeat this, you suspend, and then when you want to resume it, this process can basically make this endurance worse, essentially. People have observed that. Question? Yeah, these are some, as I said, summary of some of the optimizations that we have. But there are also many other optimizations that people have developed. Okay, let's see. Yeah, I have 240 slides. But it's good. The good thing is that the last 2 items, I/O scheduling and flash memory array parallelism, I can actually teach them quite fast. But this part needs to, go with a slow pace in order to, we all follow the topic. Any question before we jump to address mapping? Okay. So we almost discussed it actually. Like in SSC, we have the flash translation layer, also called as SSC firmware. And that provides backward compatibility with the traditional hard disk drive by hiding unique characteristics of NAND flash memory. So there are responsible, this FTL is responsible for many important SSC management tasks. We're going to discuss about address translation and plus garbage collection, which is actually essential for performing out-of-place writes. It also does word leveling and data refreshing and I/O scheduling. Today, we're going to see address translation and hopefully I/O scheduling. Word leveling, we're not going to cover, and data refresh, we're going to cover a little bit tomorrow, hopefully. So this is a simple SSC architecture that the host actually realized that the storage view at the operation system level is a flat block device. Assuming that we have here, as an example, we have 16 blocks, and each of them is a logical block address. But at the hardware, we have physical block address. So these are Assuming again we have here we have only one NAND flash chip and we have only one plane. So we want to keep things simple in this example. So we have a physical block address, and each of these pages they called as physical page address. So this is the terminology that you need to get used to it. It's also sometimes quite confusing because at the OS, at the host, we call it block address, but essentially it's actually page address at the SSD. So you need to get used to this terminology. That's very unfortunate as well. And you can see that we have actually extra space in our storage. And that's what we usually have. Like if you have a SSD that you know is 1 terabyte, your SSD actual space is actually much larger than 1 terabyte. And there are some reserved pages that they are used because of these out of place update things. So here also we have this over provisioning because as we discussed which is quite important for performance and lifetime. Okay, so now let's see what's happening when we have write request. So we have this write request A. So we want to, this is a request that we send to the flash translation layer essentially. So the logical block address is 0, like this is the offset, and the size is 1. So we just want to write 1 block address, and the direction is also right, and the value is A. So that's the request that we send to the HIL essentially, and HIL translate and send this to the FTA. So in the hardware, in the SSD backend, we write this A value in block 0 and page 0. So things are okay at this moment. Here also we are assuming that logical block size is equals to physical page size. So, but usually logical block size here is 4 kilobyte, but physical page size is 16 kilobyte. That we're gonna also see about fine-grained mapping. But here for simplicity, we consider that these two are the same size. So that's 4 kilobyte, and here is also 4 kilobyte. Okay. So later on, we also receive another request, which is the offset is logical block address 4, but the size is 12. So we want to write to 12 blocks. And also direction is right, and these are the values. So we call it as a sequential large write, for example. So when you look at your SSD backend, you can see that, okay, this is 4, this is also 4, so it would be good. You know, I will just write from 4 to 15 here, right? Because things are fine if you do that. But the thing is that that's not happening. And SSD just writes, you know, continue writing to the same block. And when block 0 is full, then goes to block 1 and block 2 and block 3. So that's the way we write. Why? Because one of them is actually, the reason is active block. So one of the block which is ready to write, meaning that is already erased and you're using that block to write. So that's your write point. We want to keep the number of write block like as low as possible. Ideally, we want to keep only 1 block being written. And this is due to the problem that we call it open block problem. So once you keep your block open, that can cause some reliability issues for the pages that we have written already in that block. So as the more you keep that, the longer you keep that block open, you can actually cause more reliability issues to those pages. So that's why you have 1 active block, you want to write to it and get it done, and then close it, and then go to another active block. Sometimes actually even flash like controller just write some dummy things, you know, to that block just to get rid of that block. Make sure that they don't, you know, issue errors like reliability issues. Yeah. Maybe, do you have something to add? Yeah, give it to Rakesh.
My question was that why do we need to write dummy data to different pages to close an active block? Why not just keep them empty and move on to the newer blocks?
So there are some disturbances that are caused when the block is active and it is still having some word lines empty. So these are not characterized yet in research works, but these are known in the commercial SSD. So that's the reason why we always program the blocks and close it. Thanks.
Okay. Yeah, so another issue is also program sequence constraint. You have this fixed program order within a block due to cell-to-cell interference. We're going to actually, here we don't have that issue actually, because you are actually writing sequentially. So you write B, C, D, and then go. But the thing is that you cannot, for example, write to page 2, for example, and then later on you want to write to page 1. That can cause some issues. So you always want to keep the order. That's even that's actually more a problem for MLC NAND flash chips. People have observed issues when we have MLC NAND flash chips. We really need to keep this ordering things. In SLC we have less issues, but still you want to obey this program sequence constraint. Okay, so now we have this problem that logical block address or logical page address does not match the physical page address. So when we receive a read from read operation for logical block address 4, we don't know where it is stored. So that's why we need to keep this table, mapping table. And for that, we need to know that for logical page address 4, we store it to physical page address 1. So we just query this table. And then we get the address for the physical page address, and then we can access the NAND flash chips. Right? Okay. So now assume that we receive some updates on logical block address A. So you receive this update with the A prime. So here what we can do is actually writing, we are doing out of place update. So our active block is actually block 3, and the next page is free, so we just write A prime here. And then we need to update this mapping table. And this one needs to be invalid. This is also important that you make this invalid. Yes? Yes. Yes. Yeah. So that's, yeah, exactly. Logical block address and here logical page address. They are the same here, especially because in our example, block and page, they have the same size here. So we consider 4 kilobyte size here, and page also we consider 4 kilobyte. If they have some mismatch, you need to be careful. Then we're gonna see actually in our next example, like in fine-grained mapping. Yes. No, you need to keep actually, we're gonna see actually, you need to keep a status stable, especially for every block. So you invalid this block 0, this page 0 in block 0, and then you get another update. You write it to 14, and then you make the previous one invalid. Then another update, and at some point, you are running out of free pages. You don't wait until all pages have been written and then you say, oh, what can I do? You really need to be a bit proactive. And once you have some, you can see that you have not many pages, remain. You need to basically call for this operation, which is garbage collection. So what does garbage collection does? What does garbage collection do is essentially we have some wasted space because of these invalid pages, right? So you can think of it like that. You want to get rid of these invalid pages to erase that block and make that block ready for future writes. So that operation, we call it as a reclaims free pages by erasing invalid pages. But the problem is that erased unit is at block. So we need to come up with a victim block. And that victim block can have also some valid pages, right? You first need to copy all the valid pages to other free pages. And then you can erase that block. So now you can actually see the performance overhead of garbage collection. Performance overhead of garbage collection is actually dominated by the copy. It's not actually dominated by the erasing operation. Erasing operation is not that much. But for all the valid pages that you have, you need to spend like read and program, because for every page, every valid page that you have, you need to read it, and then you need to program it. So you have T read plus T program times number of valid pages. And also it has lifetime overhead, so you have additional writes, which can cause program erase cycle increase. This is actually known as write amplification. This is a known metric for SSDs that people report, what is the write amplification for my device, essentially. So in hard disk drive, there is not such a thing, right? The number of writes that you have to the number of writes that you send to your hard disk drive is the same of the number of writes that you have internally, right? But for SSD, you can actually calculate that I send like 1 million writes, for example, to my SSD, but internally, my SSD, I don't know, wrote 1,200,000 writes because of these operations. Now you have some write amplification. And the more, the larger write amplification you have, it shows that your SSD, needs to do doing a lot of aging things, because of program erase and also the performance issues. So you always want to keep that write amplification as low as possible. Okay, so one of the policy for garbage collection is called greedy victim selection policy. You erase the block with the largest number of invalid pages. You just search and select the block with the largest number of invalid pages as a victim. And the idea is simple, because you can see that that block has less number of valid pages. So hopefully you can reduce the copy latency for that. So now you need to add this status table, which is per physical block address. We need to keep the status. Like for every page in that block address, you need to know if it is free, valid, or invalid. And with that information, you can now select the victim. So here in our example, block 3 has largest number of invalid pages, so we consider it as a victim. So now you need to copy the valid pages that you have here. So you have only one valid page, which is M. So you read the physical page address 12. Then you write it, program it to 3 pages that you have still. So you write M here. And then you need to update the status. So block 3 now is completely invalid. And block 4, now you have 2 valid and 2 free pages. So you update. Now you need to update the mapping also for this 15, for this M thing. So in the past, this value M has been mapped to logical page address 15 was mapped to physical page address 12, but now you need to map it to 17, right? So how you can get that information? Because it's a backward thing, right? So previously we know the logical, page address, and we access this mapping table to get the physical page address. But here is the opposite way around. You know the physical page address, but you want to get the logical page address. Okay. So for that, first of all, you can actually have another table for physical to logical mapping. But people do that as they store it in each physical page out of band area. So we show that for every page, we have some alpha bits, right? That we use those metadata essentially. So you can store that logical information, like the P2L, like the physical to logical mapping, as some additional bits to the page, essentially. So when you write to the flash, you also write what was the logical address for my basically for my block, for my data. Okay. So now that you know that block tree is completely invalid, you can just erase it. And then you can update the status of block tree that all pages are free now that you can write. It's also important to say that this erasing happening is, we call it as a lazy operation, lazy erase. So once you make it completely invalid, you don't erase it immediately. You wait until you really need it. And that's also because of open block problem. Because once you erase a block, you make that block ready to write. And you don't want to do that. You want to just make it ready to write when you really need it. So you delay the erasing operation until you need it, because we issue the garbage collection, sooner than we really need it. So you have a block with, you can easily erase it, but you wait until you really need to erase it. And that's also important for reliability issues. So you can now guess that garbage collection has performance issues. We have high latency because of all these copies. So assuming that our block size is usually large. The block can contain, for example, 576 pages in one of the prototype, one of the devices. And assuming that we have only 5% of the page in the victim block are valid. This is not a significant number, right? But 5% of this number is actually around 28 pages, meaning that you need to copy 28 pages, and it causes, like, the GC latency would be greater than 28 times TR plus T program plus T race, which is here in this example is around 27 milliseconds. And you can see that this is significantly larger than erasing time. So that's why I'm saying that erasing is actually not the dominant factor here. The copying is actually dominant. And that's why this grading policy makes some sense, because you really want to reduce that copy latency. You are selecting a block with less number of active pages in order to reduce the copy latency. But at the same time, you can also improve GC by, you can improve the copy latency by doing multiplaying operations. So then you can have some other, basically ways to, like, trade-offs to handle. Like you might select a block which actually is not has the largest number of invalid pages, but you select that because it can provide multiplying operations for you. So you have a trade-off here, because multiplying operations provide better bandwidth for you, but at the same time you want to also reduce the number of copy that you want to do. So you have two kind of, let's say, parameters here to play with, but there might be some other things as well. Okay. So if FTL performs garbage collection in an atomic manner, like once FTL starts garbage collection, it does not really service anything. Things should be done and then can basically service things. Then it can delay user requests for a significantly long time. And that was the case actually for traditional SSDs. Today, actually, we don't really observe that kind of dramatic slowdown in our accesses. So in the past, it was like you send requests to your SSD and your throughput is at this level. And at some point, GC has invoked, and you can see that the performance was here, like, dramatic difference. But now in the modern SSD, you don't really see that dramatic reduce, because vendors actually have worked a lot to reduce garbage collection. And one of the ways is also to make it not atomic, like do these suspension things. You can suspend, for example, GC and service some of the requests and then continue with your GC. There are some mitigation techniques. One of them is a trim command, which is at the OS level. So when you, for example, at the OS, at the file system, you just delete a file, previously, your file system does not really inform SSD that this file is done, and your SSD will consider that file as a valid page and will just, copy all the time. But the thing is that now with this command that people have developed for operating system, for Linux, and people actually have done a lot of research at the OS when we move to SSD, because when we move to SSD, people have been using techniques that we have been using all the time for hard disk drive, like the IO scheduling, all these commands. But at some point, say that, okay, now I have a new device, characteristics is different, so I need to also optimize them. So people come up with new techniques. Train is actually one of them. That essentially you inform the FTL of deletion or deallocation of a logical block. And then FTL can consider that as an invalid page, essentially, and it can skip copy for that. Another way is to do GC at background. So you exploit SSD idle time. Then the question is that, how accurately I can assess idle time. Vamanan, for example, has been working on that direction in his master thesis, semester project. Yeah, he's been working on how accurately we can actually assess idle time using learning techniques or things like that. But it's still, it's not really easy, especially if you consider that your SSD is placed in a cloud, in a storage system that many applications are accessing your storage, essentially. And also another issue is that when you do background GC, you may do premature GC. So you copy pages that could have been invalidated by the host system. Because you do GC sometimes premature, you are considered that some pages are valid, but those pages could have been invalidated using trim command if you do the garbage collection in a right moment, essentially. But another important technique is actually progressive GC, which you divide GC process into subtasks. Like, for example, copying 28 pages, you copy one page, and then service user request. And then you can consider like the 28 times of it, right? You do one copy and some service, and then copy service. So you're not doing garbage collection in an atomic way. And this is actually quite effective at decreasing tail latency of garbage collection. Question? Okay, let's get a 5-minute break. Then we can continue with fine-grained mapping until 3:33. Okay. Let's get started. So we talk about mapping, and we say that in our example, we consider that we have same sizes, like IO block size is 4 kilobyte, and physical page size is also 4 kilobyte. But essentially, we have this IO mismatch, and in SSD is always, is around 16 kilobyte for most of SSDs. There are some SSDs that they are performance optimized, and they are using actually lower page sizes, like 2 kilobyte or 4 kilobyte. But most of SSDs that we use today they have 16 kilobyte. So now we want to see how we can handle a small write request. So let's walk through it with some example. Like, okay, so we have inefficiency due to erase before write property, right? This is a request, logic block address 4, and size is 1, and direction is write, and data that we want to write is A. And this is also your logical page address to physical page address. So you first need to put this, logical block address to, like the binary. So, and then you can use the, since you know that your page is 16 kilobyte, you can actually use the first 2 bits as an offset. You know that which 4 kilobyte page you are writing in that physical page address. So here we know that like the offset is 0, and then the rest is actually page number. You use that the rest as a page number. So now when we want to access this logical to physical mapping, we go to this one, which is the logical page address 1. And then we write here as the offset. So we try to keep the offset the same. So since the offset here is 0, we also write here at the offset 0. That makes things simpler. So you can also write a, like for example here, but then you need to keep that information that, oh, the offset was 0, but I write it to offset 1, for example. And then here you need to keep the physical page address, which is 0 again. So far, so good, right? Then we get another request to logical block address 1, and the size is 2, so we want to write 2 pages, essentially, B and C. So you put it in the binary, and you can see that the logical page number is 0, and the offset is 0, 1, but you want to write 2, so you need to use the offset 0, 1 and 1, 0, essentially. So yeah, you need to write to the next physical page address, and the same offset, and you update this mapping. Now, the question is that why at the middle of the page? We already discussed about it, to keep the 4 kilobyte offset. Another is that why not using the unused space in the physical page 0? So the reason for that is that you have already actually allocated that space to logical block address 5 to 7. Remember that we map logical block address 4 to this physical page address. So when you map 4, that means that you are also mapping 5, 6, and 7 to that physical page address, because you need to keep the whole offset, basically, the other 3 offsets also in that physical page address. So that's one of the reasons. And another reason is that this actually has been already most probably programmed because of the program sequence. And the program sequence order. So you write this A, and you write BC, and later on, if you also receive some other writes, maybe we actually have it. Yes, we have it actually. So we have this logical block address 7, and we want to write it So you can see that this is the same thing, right? You have this logical page address of 1, and then this is a kilobyte, like the offset. So you can think of reusing the same mapping entry, right? So ideally, you can use this physical page address and you just write here. But that would actually, invalidate, like that can cause out of order programming. Because you program first physical page address 0, and then you program physical page address 1, and now you want to get back to physical page address 0 for this program. So that can cause issues. So this is I already mentioned the second reason, program order constraint. There's also another reason, which is data randomization, that cells in the unused space have been already programmed, essentially. Which, I mean, you may not also, you can also you can ignore them and you don't program, but likely you have already programmed because that's the way that Flash controller works. If you want to handle writes in a way that we were doing in the past, like we are doing this logical page address and physical page address, like the mapping table granularity is actually per logical block address. So now you can see that we have this unused yet discarded. And I also didn't say that, but this new write that you receive, you actually need to write it to another physical page address. And meaning that you also need to write this A to that as well. So you need to copy A and then D and then write it to another physical page address. So you like to avoid such things. And that's what we do with basically by using this fine-grained mapping. Yeah, I wanted to say this essentially. You read A and you also modify the part D and then you write it to another physical page address. And you also need to update this mapping table. So essentially, small writes cause read modify writes. You need to read and modify and then write it, which wastes P cycles plus additional read operations, which can cause performance and lifetime degradation. So the way that we handle it, we are using fine-grained mapping plus page buffer. So you need to add page buffer, and also here you keep the mapping at the fine-grained, like at the logical page address. So when you get this request, logical block address 0, logical block address 4, you also keep the mapping here. So you don't consider any offset here. You just go to the logical page address 4. So now you have this fine-grained mapping. Like each entry here is associated to 4 kilobyte, not 16 kilobyte. That's why we call it fine-grained mapping. And you write this value in the page buffer. And then you can also update the physical page address here, but you can also, you can leave it for now. And when you really want to write it to the SSD, to the NAND flash memory, you can update it. But for now, you can also leave it. Then for the second write that you get, you again access your page buffer and write them, B and C. And these two, logical page address, you need to also update the physical page address. Now you say that the physical page address is 1. You can see that this is fine-grained, right? Meaning that each of these fine-grained pages, they have address. So you don't use one address for all of them. So here, this address has 0, this one has address 1. So you map the second one to also page address, physical page address 1. And this third read that you receive for D, you also go to this page, this logical page address 7, and you map it to 3. So now that you have your page buffer full, ABCD, you can just flush it to the NAND flash memory. And that's how we handle these small writes using fine-grained mapping, because we need fine-grained mapping, this table, with the also page buffer that we have. Yes. Say it again, sorry, I was looking.
So let's say
Mm-hmm.
and query B is supposed to be mapped to
So, but yeah, but that's an update, right? If we want to update logical block address, so for the you are saying that for D you want to write it to C, right? Meaning that the write request is going to the same address.
not the same. For example,
Yes.
if say the D was assigned was supposed to get
But why should I do that?
if the request was
No, but that's request is actually coming from the host, and that has only logical block. So we are assigning physical page address. Question. Okay. So fine-grained mapping significantly reduces the number of NAND flash operations. You can see that 3 writes plus 1 read that we had in the previous example, and now we have only 1 write. But of course, it caused a larger mapping table. Now you need to keep mapping for 4 kilobytes, meaning that we need 4 bytes per 4 kilobyte page, and that 0.1% is coming from here. And yeah, also you should also consider this data durability of written data. Like page buffers are implemented by using volatile memory, like SRAM or DRAM. So we need to make sure that our data doesn't get lost because of sudden power off, and that's why we need to have these power capacitors. Measurements are okay with this room, but I don't know. Sometimes I don't feel good in this room. Are you guys feeling okay? Good, okay. Yeah, but despite non-negligible drawbacks and overheads of fine-grained mapping, this actually has been used significantly in enterprise SSDs. Mobile SSDs might not actually use it because they really need to keep costs low. But enterprise SSDs, they are all using this fine-grained mapping. Okay. Now let's also quickly see how we can basically. So we know that a multi-plane operation is good, but how we can ensure we can benefit from multi-plane operation? That's also another important. This is a recap about multi-plane operation that you already know. So to perform in order to perform as many multi-plane operations as possible, we need to flush number of plane pages at once after buffering them. So we use this page buffer, and we need to wait for more writes. And now that it's full, we can flush it to the NAND flash memory. And that's we can benefit from multi-plane operations. And so on and so forth. So then we have this definition of Superblock-based block management. So you consider the whole, like all these planes, consider them as a superblock and try to manage your superblock whenever you want to erase it or do garbage collection, whatever. And that superblock can actually basically go to other flash chips as well. So you don't only consider one die, you also consider several dies and several flash chips. And you make a big superblock and try to manage it. Because if you manage a superblock nicely, you can benefit from parallelism as much as possible. You can send requests in parallel. But let's see what would happen if we, for example, do garbage collection, first oblivious of this multi-plane operation, and then aware of that. So this what we already know, right? For reducing performance overhead of garbage collection, we want to have this greedy policy, and we select the blocks with the largest number of invalid pages. This is the plane, and after some time, we know that these are the number of invalid pages that we have per block. So we know this block is invalid, like the number of invalid pages is higher, so we consider as a victim selection. And we need to copy valid pages to the block n-1. And then we can erase block 2 and make it basically ready for future writes. Now consider that we have 2 planes, and we want to apply the same policy here. So in these 2 planes, basically now you also have the number of invalid pages per each of these blocks. You can see that this block 1 in plane 1 has the largest number of invalid pages, and block 2 here has the largest number of invalid pages. So now we have this issue. In multi-plane system, these 2 blocks that you want to consider them as victim, they are not aligned, meaning that you cannot really benefit from multi-plane operations. So once you want to do copy, you need to do single plane read. And here also you need to do single plane read. So here you need to do actually 3 reads, but 1 read. Here also 1 single plane read. But at the block n-1, you can actually do multi-plane write. So you do read these 2, put them on the page buffer, and then you do multi-plane write to that block n-1. And in addition to that, you need to also do 2 single plane reads and 2 single plane writes for block 2 here. So you can see that we had 4-page copy. So that's the number of copies that we had. But after all, we had 4-page copies, like 3 reads here and 1 read here. And we could have done it with only 2 multi-plane reads and 2 multi-plane writes, essentially. And that's also not the only issue here, is that block n-1, now the write point is actually, the write point for block n-1 in plane 0 is here. And the write point for plane 1 is actually here. So you cannot also benefit from multi-plane operation in the future as long as you don't discard. So there is a way that you can discard these 2 free pages here in plane 1, such that you can benefit from multi-plane operations in the future. Is that clear? Okay, good. Okay, but when we consider super block-based management, we group each block with the same index as a vertical position in different planes. So now we try to select a block, like a super block, with the largest number of invalid pages. So here we can see that block 1 has, in total, has 9 invalid pages. If you consider like a super block, so now we can, that's our victim block essentially. And these are the valid pages that you need to copy essentially here. So you can see that block 1 actually has a lot of valid pages in plane 0, but in plane 1, it has only 1 valid pages. So you can actually check these equation numbers at home if you want, essentially, but essentially for some of them you can do single read, for some of them you need to do multi-plane read. But essentially you can benefit from a lot of multi-plane operations. And at the block n-1 also you can do multi-plane writes. The pros is that you can keep performing multi-plane writes, but at the cons you need to, in this specific example, you need to do more read and write operations. So in the end, it's not really clear which one is better. Yes. No, we don't move from plane 0 to plane 1, no. No, yeah, you're right, actually, yes. You can actually benefit. You can move things from plane 0 to plane 1. Yes, that's true. Yeah. Correct. Yes, exactly. Yeah. And it's not clear actually which one is better but you should also consider future accesses. So once you have this Superblock access, hopefully in the future, you can actually service more multi-plane operations. Yeah. And as I said, this Superblock can, you can do it at the die level or SSD level. There are actually papers that try to make a Superblock, not even vertically, they do this. There are many things going on in that line, essentially. Okay. Let's see. I will explain very quickly IO scheduling, but I will make the rest for tomorrow. I think I can finish IO scheduling 6 minutes, 6 or 7 minutes. So we discussed about FTL operations, and IO scheduling is one of them. For this, I'm going to use this paper, Flynn, that we have published in ISCA 2018, enabling fairness and enhancing performance in modern NVMe SSDs. So in modern SSDs, use new storage protocols like NVMe that eliminates the OS software stack. I'm going to show it actually better in this picture. You know all these stuff like backend, front end. I'm not going to go over them. But this is essentially what NVMe is. So in SSDs, in the past, initially adopted conventional host interface protocol, SATA, that we have been used for HDDs. And that is basically is like each process has a IO request queue at the OS software stack. So each process has a queue at the OS software stack, and then OS software stack needs to combine all these queue, somehow schedule them, and then send them to the SSD device as a hardware dispatch queue. So that's what we have in SATA, essentially. But people have realized that this doesn't really work well for NVMe, for SSDs, because SSDs have actually they can provide very good throughput, and this SATA actually can limit the throughput. So in order to overcome that, people come up with another protocol, which we call it NVMe, which is high performance host interface protocol. And the way that we handle it is that they remove this OS software stack completely, and they map all these queues directly to the SSD device. So now essentially each process can have a queue internally inside the SSD, and each process can actually write to that queue using actual user level code, not even at the OS level code. So OS needs to be involved in order to each process initiate a queue, in the SSD device. But once the queue is initiated, the process can write to that queue using user level code. And that can make things very fast, because NVMe is also implemented using PCI Express, which is PCI Express provides a lot of bandwidth, and NVMe is a way to benefit from that bandwidth. So you can also implement NVMe on using other protocol as well, like other hardware protocol, because NVMe is actually is a software protocol, it's not a hardware protocol. But in order to get benefit from NVMe, you really need to implement it on the PCI Express or M2 for mobile systems, for example. Is that clear? Now you can see that when we map this queue to the SSD device and there is no OS, so no one is doing that scheduling stuff. Then you can guess actually that we have fairness issues. So in the past, OS was somehow handling basically fairness using that IO scheduling. But now there is no IO scheduling going on at the OS level. Everything is happening at the SSD, and that can cause fairness issues. But at the same time, when you are doing IOS, when you have access to your SSD, so assuming that you can implement IO scheduling inside the SSD, now you have much more information about this process. You know about the internal parallelism, internal task of the SSD, so you can hopefully make a good decisions, make much better decision as before. So you can see that opportunities and limitations. So when you move to this NVMe, you don't really have anything IO scheduling at the OS level, which can cause issues. But now you have some opportunity to benefit inside the storage in order to implement IO scheduling, which is even better compared to OS level IO scheduling techniques. So we have done some experiment on real systems, and we define some metric for slowdown and unfairness. You can see that we come up with the terminology, like this is not actually our terminology. Like flow is a series of IO requests generated by an application, like a flow of them, like a series of them. And we consider a slowdown as a metric, like which is we run this flow alone, and we capture the response time of that. And we also run this flow in a shared manner, and we calculate the response time, like measure the response time. And a slowdown is essentially shared flow response time divided by alone flow response time. Clearly, lower is better. And unfairness is maximum slowdown divided by minimum slowdown. And you can see that, again, lower is better. And fairness is basically reverse of unfairness. And higher is better. So we have done an experiment on these two workloads, TPCC and TPCE. So TPCC is considered as one of the workloads that is not really. So you can see that TPCC doesn't experience much slowdown when it's run together with TPCE, but TPCE actually has experienced a lot of slowdown. These are like some transactional database transaction workloads. And as a result, we have very low fairness. So our takeaway was that SSDs do not provide fairness among concurrently running flows. We discussed different reasons that can cause this issue. One source is different IO intensities, like when you have the IO intensity of a flow affects the average queue wait time of flash transactions. I'm gonna conclude in a few minutes, and then because we also need to get to seminar class. Or maybe I can wait it for tomorrow because I don't want to waste it. Let's continue from the sources tomorrow. Any questions? Thank you. See you tomorrow.